Wanted to work through a problem that involves photoelectric effect. So the photoelectric effect is that when light is shone onto a metal, electrons are liberated, emitted by the metal. And the way that we understand the photoelectric effect is not by thinking of light as a wave, but rather by thinking of light as particles. So the photoelectric effect was important in revealing this sort of wave particle duality of light, that it exhibits both particle-like properties and wave-like properties. So in this particular problem, we're asked to imagine two metals. One is lithium and one is mercury. And we're told the wave functions of the lithium and the mercury. And the wave function of lithium is 2.3 electron volts. The wave function of the mercury is 4.5 electron volts. The wave function is an amount of energy. It's an amount of energy that's needed to release an electron from the metal. So in lithium, it takes 2.3 electron volts to release or liberate an electron from the metal. In the mercury, it takes 4.5 electron volts to release or liberate an electron from mercury. We're also told that we shine light on the lithium and the mercury, and we shine light with a wavelength of 400 nanometers on the lithium and the mercury. And we're asked whether that wavelength of light liberates electrons from the two different metals. And if it does liberate electrons from a metal, we're asked what is the maximum kinetic energy of those electrons. And so we're going to go through those two parts of the question. First, figuring out whether that particular wavelength of light does liberate electrons, and then we can ask the question of what is the kinetic energy of those electrons. So the first thing I'm going to do is calculate the energy of a photon, a packet of electromagnetic radiation, a particle of electromagnetic radiation that corresponds to 400 nanometer light. And the way I'm going to do that is with the equation that Planck-Einstein introduced, that the energy of a packet of light, a particle of light, a photon of light, is equal to Planck's constant times the corresponding frequency of that light. And in this case, because we don't know the frequency, we know the wavelength, we'll just replace this frequency here with the wavelength. We'll write that frequency as the speed of light divided by the wavelength. So this equation here, this replacement of frequency with speed divided by wavelength, is just using that equation that the speed of a light ray is equal to the product of its wavelength and its frequency. Well, at this point, we know Planck's constant, or we can look it up. We know the speed of light, we can look that up, and we're told the wavelength of the light. So these three numbers, h, c, and lambda, we can plug them all in. So let's do that. The value of Planck's constant is 4.14 times 10 to the minus 15 electron volts seconds. So plug that in. The speed of light, 3 times 10 to the 8 meters per second. Plug that in. And then the wavelength of the light, that's 400 nanometers. That's 4 times 10 to the minus 7 meters. Plug that in. And if I go ahead and calculate, I get 3.1 electron volts. And so that's the energy of a photon for light with a wavelength of 400 nanometers. So once you know the photon energies, or the energy of the photons that we're shining onto the two different metals, You can compare that with the work functions of the two different metals and determine whether those metals do or do not emit photoelectrons. 3.1 eV is greater than the lithium work function. And so lithium does emit photoelectrons with this wavelength light. 3.1 eV is smaller than the mercury work function. So mercury does not emit photoelectrons with this light. So let me just write that down. So the lithium emits electrons because the photons have a greater energy than the work function. And the mercury doesn't emit electrons because the energy of the photons is smaller than the work function. So we can go ahead now and calculate the kinetic energy, the maximum kinetic energy of the electrons emitted by the lithium. There's no such calculation for the mercury because no electrons are emitted. So the maximum kinetic energy is just the difference between the energy that's carried in by each photon and the energy that's needed to remove an electron from the metal. That energy that's carried in by each photon, that was HF, and we've already calculated that. And then the work function, we were told in the problem. So the energy of the photons was 3.1 electron volts. The work function of the lithium was 2.3 electron volts. And this I can do in my head. This gives me 0.8 electron volts as the maximum kinetic energy of the electrons that are emitted when 400 nanometer light is shone on the lithium. Anyway, that's an example of the photoelectric effect. It was a very important process in uncovering, revealing this wave-particle duality of light, that it comes in packets, that it comes as particles, comes as photons.